Hello everyone. So we got a few questions via email. Well, I got a few questions via email. So I'm going to try and answer them in this short, hopefully short little video. Okay, so first question is a question about example 8-6 in the book. So on page 342, statistical physics. The question is about the statistical distribution of helium in the atmosphere. So we're using this equation here, number of particles over volume, 3m kt 3/2, and under Planck's constant cubed, much less than 1. So this equation is what we use when we want to find out if we can use a classical distribution or if we have to use one of the two quantum mechanical distributions. So in the example, basically we're plugging in some numbers into this equation. So I'll write out all those numbers and then I'll identify them. So 3 times. Okay, so this n over v that's given in the previous step of the example, and that's this number here, 1.41 times 10 to the 20th. So that's that nv there. This is clearly Planck's constant cubed. This guy here, that is that 3m, and then this is the kt. So that 3 is this 3, obviously. And then the question that I got about this example was that where is this 4 coming from? Well, that 4 gives us, together with this number here, that's the mass of a helium atom. So electrons, their mass is negligible compared to a nucleon. And nucleons have about the same mass. Neutrons and protons, their mass only differs in the third decimal place. So that's just ignored here. So 1.66 times 10 to the negative 27, mass of nucleon times 4. So that we had 4 nucleons in the helium atom. So that was the first question. I'm going to go look at the second one. Next question was about when we have to use Fermi statistics or Boltzmann, not Boltzmann, what's the other B word? Bose-Einstein, haha. Bose-Einstein or Fermi-Dirac statistics, in the sense that at what point can we no longer distinguish between two fermions or two bosons? You might say, well, if I have one way over here and one way over here, I can clearly say the one on the left or the one on the right. So at what point do we say that they're indistinguishable? And they become indistinguishable when they enter within their own de Broglie wavelength. So remember that this wavelength is the wavelength characteristic of an individual particle, and once two fundamental particles are within their de Broglie wavelength of each other, we can no longer tell which one is which, right? Their wave functions are in a sense overlapped, okay? So we can't say that afterwards, right, that this one is this one and this one is this one. We don't know which one is which, and in a sense, nature also does not have that information, right? This is something that can't be known, and the condition for that is that they are within their de Broglie wavelength of each other, and that they're the same type of particle, electron or proton or whatever else. Of course, if we're talking about fermions, spin 1/2 particles, right? They can't get so close to one another because they can't be in the same quantum state, right? Unless they have some other quantum number that's different, right? So if this was an electron spin up and spin up, they wouldn't be allowed to be within their own Rayleigh wavelength of each other. That would be the Pauli exclusion principle coming into play. But if one is spin up and the other is spin down, then they can, right? And of course, they could also occupy the same orbital of an atom. Okay, gotta go look at the next question. Okay, next question is about one of the steps in one of the calculations from lecture number 15. So this is when we're calculating density of states. So, question was specific. Well, I'll draw the little picture because that's probably helpful. Right, so we're calculating density of states of n classical particles in a box, right? So, you know, if we have a particle in a box, right, we have an excitation in each possible dimension, right? So the transverse can be excited, the longitudinal, the depth, or whatever you want to call it. So that excitation number we just plot out as a coordinate. So this would be how many excitations we have in y and z and in x. And because these excitations are discrete, we sort of fill out this space with a little cubes, right? And these little cubes, I mean, if you want to look 343 in the book, has a better picture. Let me just show it to you right there. This is what I'm trying to draw, right? But we make the assumption that the spacing between these energy levels is so tiny compared to the possible number of energy levels that we say that this can be parameterized by some r, right? So, in effect, the volume of this little octant of a sphere that occupies this octant of R3, right? That tells us how many states we have, the density of the states. Okay, and again, we're ignoring like this little discretization because we're saying that this R is so large compared to this little distance here. Okay, so then the question was, when calculating the number of states, we start off just calculating the volume times 1/8, and then for pi r cubed. So this volume is a sphere. This is 1/8 of it. And then the question is, how do we get to the next line? Pi over 6 e divided by e naught 3 halves. Okay. Oh, I need to think about this, I think. Hold on. Okay, that one quick. So where that comes from is if you look on the previous page in the book, we have equation 8.38. I'm just gonna clear up some space up here. And this equation says E equals E naught nx squared plus ny squared plus nz squared. So the square root of this is going to be our r, right? Because we're talking about, well, I guess I could draw that back in. We're talking about this radius here, this radius r, which of course is then just flat if we have one dimension, right? So we're talking about this radius r, which if we're talking about the dimensions nx, or ny, nz, and x, this distance r is going to be square root nx squared. I'll write it this way. Oh, no, I'm just writing the same thing again. That's not helpful. This is just Pythagoras' theorem, right? So this is r squared. Because r would be the square root of that, right? Just the Pythagorean. Oh God, it's gotten so bright. I can't. Okay. The sun keeps coming in and out Someone, Jack, suggested that I put the light source behind the camera, but then I tried that, but there's too much glare then on the whiteboard and you can't see it, so I guess we're stuck with this right now. Right, so we've got r squared here. Well, actually, right, this. So we got r squared there because this is how many notches over we're going, and this is how big each notch is. So that E naught is going to be that distance here between 0, which is a state we can't occupy, and the first excited state. So that first excited state, if it was this guy here, it would be nx equals 1, 0, 0. So then that gives us this line down here, right? Because we got this cube, that's that cube there, and this square root, that's the square root we get from this actually being the r squared, not the r. Okay. Yeah. So we're just subbing in this guy for this guy, and of course this E naught gets moved over there. Okay. Next question. Okay, the next question is about one of the problems from the homework, problem number 33 in chapter 11. Beryllium-8 is very unusual among low Z nuclides. It decays by emitting 2 alpha particles. Show why beryllium is unstable towards alpha decay. Okay, so this is a difficult problem to sort of suss out, but if we look at the binding energy of beryllium versus the binding energy of 2 isolated helium-4 atoms, right? If you calculate those 2 binding energies, you'll see that the 2 isolated beryllium-4 atoms have more binding energy than, what did I say? I'll just start again because I don't remember what I said. What was I saying? If you calculate the binding energy of the beryllium atom and compare that to 2 isolated helium-4 atoms, you'll see that the helium-4 atoms together have more binding energy than the beryllium atom, which of course means that because there's more energy caught up in the binding, the more tightly bound, right? So the way you would demonstrate that is to calculate the binding energy of beryllium atom and calculate the binding energy of a helium-4 atom. And I went over that when I talked about binding energy. Okay, I'm going to look at the next question. Okay, the next question is, why do we have to use degeneracy when we're talking about classical distributions? The question was, isn't degeneracy inherently a classical phenomenon? It's not. That's the short answer. Degeneracy comes up anytime different arrangements of things have the same energy, right? So trying to think of an example would be if I had if I'm looking at just an individual particle in isolation, right? It can fly this way with some velocity. It can also fly this way with some velocity. But which direction it's going in doesn't, oh God, you can not see it all really. Maybe if I sit right here. So, which direction this particle is going in doesn't affect the energy, right? It has the same energy going this way as the same energy going that way. So these 2 energy states are degenerate. Now, if we imagine that these are, electrons, that's not an electron. They're electrons, and then there's a magnetic field, right, pointing in some direction. Of course, they're going to have different energies, right? Yeah, so that would break the degeneracy. So degeneracy comes up not just in quantum physics, but also in classical physics, because when we're counting up all the different combinations that lead to the same energy, we need to take into account degenerate states. Okay, next question. Okay, 2 more quick questions. One was, have we talked about the strong nuclear force before? Before we started talking about nuclear physics specifically? And the answer is maybe. I'm not sure. I didn't leave out anything in these lectures that I assumed you had known from before. I taught everything that I thought you should know about the nuclear force in these series of lectures. So if I have talked about the nuclear force before, which perhaps I have because it's one of the 4 fundamental forces, I don't expect you to remember that, just this stuff in this chapter. Okay, and then the other question was, are you guys expected to know anything about Feynman diagrams and quarks on the exam? For Feynman diagrams, certainly not. I don't expect you to be able to use or really even understand exactly what Feynman diagrams are. It's an advanced concept. It's nice, obviously, to understand it. And as far as quarks go, if you know that a nucleon, a neutron or proton, is comprised of 3 quarks, and that these quarks within a nucleon express the direct strong nuclear force, and that individual nucleons bound together in a nucleus are a residual or composite nuclear force. And maybe if you know the name of that intermediary boson, the pion, neutral pion, and that's that. I wouldn't expect you to know anything other than that. Okay, so those are just the few questions I got. Wow, everybody's walking their dog right now. Very strange. You don't see anybody all day, and all at once there's 6 people walking their dogs. Anyway, yeah. So hopefully that was informative. Sorry I didn't get to doing this sooner. You'll have your exam, of course, on Wednesday, and then next lecture will be, I believe, on Monday, and then there's standard symposium. So then you'll have no lectures this week, right? Because I'm recording this on Monday, and there's no class, and you'll have exam on Wednesday, and then you'll have another lecture on Monday, no class Wednesday, and then the next week after that, I think we'll have our last 1 or 2 lectures. So this exam will actually sort of conclude the regular course of material in the book. I'm going to use these last final lectures after the exam to talk about some sort of special topics related to my own research in quantum information and quantum technology, which is a growing field right now, so it's interesting to sort of dip your toe into it. We'll talk about things like the idea of entanglement, foundational questions in quantum theory. Perhaps we'll go over interpretations of quantum theory, many worlds, Bohmian, Copenhagen, all that kind of stuff. So that should be a little bit of fun. And then, I will expect you to know those things, at least in the basics, when we have our final exam at the end of the semester. So it's not like you can just lay back and relax after this exam. You are still going to have to learn some stuff, and I'll come up with a homework as well. Hopefully that's everything you guys need to know. If you want to ask me other questions, send me an email. I probably won't make another one of these videos because it's time consuming, and I also have to upload it, which takes a while. But if you have a question, I'll try and be better about answering them by email. Okay, hope everyone's doing well. Talk to you soon.